Good afternoon, everyone. We're going to start right at 2 o'clock, so just allow us to have a few minutes here while we let everyone join in for this session, but thank you for joining us today. So we're about to start right at 2 o'clock. Thank you, Dr. Lee, for joining us today. 1 minute more. Oh, well, it's already 2 o'clock. So let's go ahead and start. Welcome, everyone. Thank you for joining us today for another webinar here at CSE3 in East Carolina University. Today, we have a special guest, Dr. Lee from the College of Engineering here at ECU. He's going to be talking about design of manufacturing systems for an optimal material handling. He brings a special case with a AI-based application to support manufacturing optimization in hydrogen production. My name is Marley Irby. I'm going to be the moderator of this session, and I work for the center as a pollution prevention specialist. Next slide, please. So here at the center, we are a research-driven institution. We're committed to advancing renewable energy technologies and sustainable natural resource management. We also strive to enhance public awareness through applied research and workforce development. Next slide, please. Some of the services that we do under the pollution prevention program that we manage here at ECU include these monthly webinars, workshops, and technical courses. We also support companies with cash flow and market analysis, provide technical and engineering support, and one of our most known services, which are the energy, water, and lean assessments, which, by the way, I just wanted to highlight this because ECU recently was awarded another pollution prevention grant through our center. And so we are offering free energy modeling assessments to any company here in North Carolina interested in looking for opportunities to reduce waste, reduce energy, or save resources. Please connect with us if you are interested or share this information. We would love to support your environmental goals. Next slide, please. So this webinar, just for your information, is being recorded. You're welcome to keep your cameras off. And if you want to speak at some point to ask a question, just raise your hand. We will ensure your mic is activated to ask questions to our speaker, but you can also use the chat and you can write your question there and we will address the question at the end in our Q&A section. Uh, Another thing, we appreciate your feedback, so please let us know at the end anything, any comments that you would like for us to improve the work and the services that we're doing here. So that's very welcome. Next slide, please. So today we have Dr. Jinkun Lee. He is an associate professor from the Department of Engineering at East Carolina University. He's been here since 2018. He holds a bachelor's and master's degree in aerospace engineering from Seoul National University, and more specifically, a PhD in industrial engineering and operations from Penn State. His work includes 2 years on automobile industry, 5 years in the Aerospace Research Center in South Korea. He also teaches analysis of production systems and AI application in engineering. Besides this, he also has served as a PI and co-PI with multiple industry lead projects. His current work focuses on data-driven process automation in the areas of manufacturing and healthcare device, as well as traffic road network simulation in consideration of anticipated increase of autonomous vehicles. So without further ado, I'm going to turn it over to Dr. Lee to continue your presentation. Thank you for your time, and we look forward to learn from you.
Oh, thank you, Dr. Lee. My name is Jinkun Lee. It's my pleasure to share my recent collaborative work with my colleagues. This work is actually done as the part of the PhD dissertation of Dong-wook Yang. He is in South Korea. But his advisor, Sung-im Che, and I have been working as mentoring him for dissertation faculty advisor for 2 years. So this will be summary of the collaboration with the Gwangju Institute of Technology in South Korea and also me in East Carolina University. And this content is also planned to be printed in March next month. So thankfully it was accepted well by SCI journal, and it's going to be printed out with the information below the presentation slide. So what we are going to talk is one of the application in manufacturing area, and specifically we are using AI to figure out how we can optimally operate a business or a complex system, especially for generating and storing hydrogen production system. But we are producing hydrogen from electric energy using the photovoltaic, the solar energy. So we call it green hydrogen. And we are going to talk about what's going to be the meaning of this system and what's going to be importance of this system in the future and what's the trend in South Korea and all over the world. And we are going to also show some experimental work with preliminary system data together. So the talk will be following the structure with introduction first. And I'm going to explain how we build this green hydrogen production system model. The model consists of many different modules. So I'm going to explain briefly, we are not going to deep too much, but briefly explain how each component will be simulated and modeled with coding or the data. And then finally, in the methodology part, after integrating this module as one complicated system, I'm going to explain how we determine how to operate this, when to sell, produce hydrogen and when to not, and if there is any remaining gas from remaining electricity from solar system, is it good for sell it or buy from the grid? So there's a lot of real problems are incorporated in this operation. So that's going to be discussed. But one important thing is we made this system working by AI module, artificial intelligence. So instead of deciding ourselves, given the information and criteria, what we are aiming to maximize profit or maximize the energy, environmental efficiency, whatever, depending on our goal, the AI will figure out when to produce and when to sell and when to store. So that's going to be what we call optimal operation. And section 4 will show briefly how we validate and verify and validate our model with existing data. So that's going to be, I'm not going to go too deep into this part, but just show you this model is a high fidelity model. And finally, I'm concluding with what we found and what we have done and what's the implication of it and what we are planning to do. So first, the introduction is there are a lot of necessity from the world about the hydrogen. Well, first thing is the carbon neutral or net zero. So we don't want to produce carbon because of the environmental issues. But in case of hydrogen, when we are using it as a fuel, there is no carbon atom at all. So there will be no carbon dioxide or any carbon-related byproduct after we burn it or use it as a fuel, whatever. So that's going to be the highlighted as the recent demand. And the forecasting says the demand will increase exponentially from 2030. And that's going to be just a few years later. But in next decade, few decades, it's going to be possible that one of the major source of our energy. And there is also a surplus power problem because we are using a lot of renewable energies. We have currently built plant, the grid system, and we are generating electricity from atomic fuel or hydrocarbon fuel, whatever, but that's going to be replaced by renewable energy. So there are still many remaining surplus power, and that should be, if we have remaining power, what can do with? If we keep using it and send it to the grid will be burned and there will be electric issues. So we have to trash them, all the remaining surplus powers. But in case there will be any shortage of the power, we are going to experience blackout. So we are always supposed to generate more than what we need. But the more we produce, it's going to be just we have to release all of them without using anything. So because to protect the grid. So the supply power system should be also managed in somehow in balance with the renewable system. And the operation of green hydrogen system itself is a big challenging. So for one goal is we need to minimize the grid power because to generate hydrogen from water, we need electricity. And that's what we call electrolysis reaction. But to do this, if we use renewable power source to do this, it's going to be safe and free. But if there is more demand in hydrogen in the market, but we are short of the solar power or wind power, any renewable power, then we have to bring the electricity from the grid. And that means we have to pay for that. And out of this, we are going to produce the enough amount of the hydrogen to sell it or provide it to the market. But that's something we don't want to do it. So we have to make decision how much we have to bring from the grid and how we can minimize it. And other cases, if we have abundant power from renewable sources and that's remaining, we can save it temporarily from to the energy storage system, but there is also limit. So there is also chance we can sell our electricity back to the grid. So basically, this is a market. We can buy from the grid or we can sell to the grid. So that's going to be something we also want to optimize, how we can maximize the balance between the two. So this is a study from the market study from South Korea and the anticipation in 2030 2040 and 2050, and there will be more growth, expecting we are growth of the hydrogen demand in the South Korea. And in the right pane, that's going to be also the global trend related to this green hydrogen. There are going to be more demand in the future. So the sources is in the bottom with the citation. So, and that's something, the demand, we need green hydrogen, and we expect green hydrogen will be very playing an important role in the future. But next one is we did some literature review of how to optimize the system model using some AI technique. So there are a term using DRL is abbreviation of dynamic reinforcement learning. This one is after we build a dynamic model of the system, it's a kind of we are running machine learning and let this machine learn which cases it's going to improve our goal or objectives, or in which case it's going to be the opposite direction. So by this training, we are going to make decision using DRL. And also, there is also planning for energy storage planning, but that's going to be also usually recently replaced by AI in many areas. From 2018 and 2015, the more AI-related application papers are published in the literature. So this is also one specific example in Brazil, the study in the Brazil. In this case, if you look at the graph in the lower right corner, there is a hydrogen requirement in the middle, but there are some solar electric power area in the north, and other green dots are grid powers. So they are using solar power during the daytime, but in the evening or in the night, when they need to generate hydrogen gas, they have to bring the power from the grid. So there was some, the left diagram shows how they are using the mixed integer linear programming approach to solve this problem. And MILP, mixed integer linear programming, is very complicated combinatorics calculation. So it takes a lot of time, and also the model should be greatly simplified to be able to solve. Otherwise, because of the course of the complexity, it's very difficult to solve the real world size problem with many nodes and many environmental parameters. So the current recent trend is solving this problem using AI. So this is a study of what kind of AI tools are available to solve this dynamic problem, especially a dynamic reinforcement learning problem. The two big categories, first one is emergency control, and that's value-based reinforcement learning. So this is the case when we need a specific value, but it's going to be dropped, or it's overheat the specific value. It's going to react quickly based on the value. So it's something like a feedback control, but have a goal, optimal goal, a global goal in above the all feedback control, simple feedback control cases. And second category is what we call operational control. That this is policy-based. So policy-based means for different situation and different environment, we are training again and again and again until we find what is good for these cases and what is good for other cases. So it's again the combinatorics with probability problems, but each cases we are going to find a policy. In these cases, do this. And in these cases, do this. So that's going to be set of a lot of combinatorial environment parameters with specific policy that proved to be most efficient or most effective. So after we build this kind of instruction set, then the machine is trained, then the machine will make a decision autonomously. In these cases, following the instruction, do this. In this case, do this. So we are not going to determine every cases, but based on the previous training, the system will able to do what they are supposed to do. And the lower right diagram is showing different algorithm in deep reinforcement learning, but the upper one is value-based, the emergency control, and the lower, the tree is showing the policy-based. And what we are going to use is one in the middle, proximal policy optimization, PPO, and A to C, actor critic method. We are going to use these two, and I'm going to explain more extensively about our application with two policies, specific policies in the bottom. So the objective of this research is first developing the model. The green hydrogen system is consists of many different modules. So we need to combine them as a system module. So renewable energy generation system prediction module and smart PCS. This one is control of the different sources of the energy from renewable power, electric battery storage, and also from grid. So that's going to work as an agent. And also price model, the price of electricity is also always changing. So when we buy from the grid, we have to pay, but the price is not fixed. It changes over time. And also we have surplus electricity from renewable energy and we want to sell it. The selling prices also changes over time in the market. So various price changes with some uncertainty. We are also making the model how we can utilize this price information. And electrolyzer is get electricity from the source power source, and changing the water into hydrogen. That's going to be the generator. So how we are going to use simulate this one, and this will be the electrolyzer module, and integration of all these module will be our green hydrogen system model. And there will be some different algorithms will be applied to make it work optimal way. And optimal operation strategic model will be also investigated. One is a deep reinforcement learning framework. That's overall a framework for dynamic system. But we also want go through the different cases, specific algorithms, and verify and validate and discuss what's the pros and cons of each. And we are going to explain why we have to choose a specific algorithm for this problem. And so that's going to be the contents of my presentation today. So second section is building this developed green hydrogen complex system. So this is a diagram of the green hydrogen system. The first left part is power generator. The solar panel provide photovoltaic electric power. So P represent the power, electricity, and voltage. And there will be combined energy storage system. So if there is good enough production of the power, part of them will be used through the PCS and used to generate hydrogen. But if there is any remaining power, that will be saved in battery. Basically, electric storage system is battery. And when it's cloudy and we do not have enough solar power, we can derive saved energy from the battery. So this will be, the left part will be working interactively with solar power and battery, but there will be renewable source part. And second part, gray part, will be the grid power that's going to be connected to the grid. And we are going to buy the electricity from the grid and use them to generate hydrogen. However, if we have remaining electricity, we can also sell to the grid. So that's going to be the market with different selling and buying prices. And water electrolyzer is basically using the electric power is changing water into hydrogen, and also oxygen. So we are going to generate hydrogen here, and we are going to model this with numerically too. And that hydrogen will be saved in a fuel cell. We will use in fuel cell also that can be used for hydrogen refueling station. And we do not have specific market with hydrogen powered vehicles or trucks, but it's going to be emerge soon, and a lot of models are in production with prototypes. So there will be a lot of application, but we do not have real market data about H2 demand. So we use this part, the utilization part. We assume what's going to be the power and how they are going to increase, and daytime, nighttime, we made some assumption. But if we can get real data about the demand, market demand of hydrogen, then that will be simply replaced with the database. So that's what our green hydrogen system. So there will be, the system modeling will be first task we need to handle is the observation of the variability in renewable energies. There are so many randomness, especially for solar and wind power. We cannot predict what's going to be its production, power production. It depends on the day, cloudy day or cloudy day or windy day or not. So renewable energy is very favorable in environmental issues, but the problem is they are very unstable. So that's going to be the problem. We have to observe the variability. So one approach we handle this one is attaching the battery, the electric storage system together into the renewable energy source that's going to working kind as a regulator. In case of there is a high power production or not, it's going to regulate the value. And second task is maximizing the system operational benefit and cost efficiency. So this is not just for research for government organization or government institute. This one is worked as a project part of the project of the real the production electric production company in South Korea. So their goal is they are not running this as a non-profit organization. They have to make profit. So they have to utilize how they can save, minimize their cost, and maximize their the profit. So that's going to be the real obstacle we have to handle and eliminate. And third one is optimization of integrated operational algorithm based on the multi-objective criteria. So while running this system, one objective is clear. We want to maximize the profit. When the selling price of the electricity high, we sell more. And when the buying electricity price is low, we are going to bring more from the grid. But one condition should be met. If there is any demand of hydrogen in the market, we have to first meet the demand, and for the remaining electricity, we can buy and sell and do something. So we want to maximize the profit, but it's not always possible. So we have to figure out what should be the optimal algorithm to do this, to, in general, in the long term, how we can make a profit. So first, we started with the renewable power module, the PV, photovoltaic solar systems, and we used long short-term memory deep learning model to anticipate what's going to be its performance during the daytime. And I will explain the real data with the verification part, but this is how the LSTM module is used to generate and figure out anticipate what's going to be its power production. So it's going to be learned with past data, the cloudy day, sunny day, the spring, summer, fall, winter. We are going to collect as much as possible. And out of this data, it's going to give us what's going to be predicted power tomorrow. But that's what we want, because without knowing this one, all other activities like the grid power and energy storage power, how we can distribute the power sources to generate hydrogen, it's going to be all affected by this main source. So this prediction of this performance is very critical. So we used a deep learning model to predict its performance in the next myopic future based on the past data. The second part is below the renewable energy, the solar panel, there was energy storage system. So SOC is the level of battery, in simple word, the state of the charge. So based on the charge level, this one is showing what's going to be the power we can derive from the electric power. And if there is any surplus power, what we are going to do, and if there is a deficit in the power, what we are going to do. So it depends on the demand in the market, how much hydrogen we have to produce. So based on this one, if photovoltaic power and saved power of battery, some of this is more than the demand of hydrogen to produce enough hydrogen, then we are going to have surplus power that can be sold to the grid. And in other cases, if our energy source is less than the demand in the market, then we have to buy electricity from the grid. So that's going to be different situation with min, max, and inequality cases, and also efficiency will be added from the literature. So this one is the model for the battery, the energy storage system. And this part will be what we call PCS, power controlling system. It's going to determine how much power we can bring from the solar panel and how much from the battery and how much to the or to from the grid. So this one is distributing the portion of electric power to generate the hydrogen. So the demand will be always the basic information, and out of this demand, we are going to subtract photovoltaic power and energy storage battery power, and this is positive. That means we need to buy the grid power. That's the case. And if this right hand side is negative, that means we are selling to the grid. So into the grid will be negative, and bringing it from the grid will be positive. So we are considering our system as a control volume, and into our control volume will be positive, and out of our control volume will be negative. That's going to be the sign convention. Right, and this one will be the next part, next module, water electrolyzer. Using the power, it's going to change water into hydrogen system, and also there will be byproduct of oxygen. So this will be using some electric system phenomena reaction, and that's going to be described by differential equation. That means if we press the turn on the power, it's not going to work directly. There will be some delay with action, and also the delay in this change of the state. So whatever we do, the water cooling pump will be up around this electrolyzer to cool down and to remove the heat from the electrolyzer, and that's going to also take some time. The reaction will be delayed. So all these phenomena will be described with differential equation, and this will be used for modeling electrolyzer. And next one, this one is showing it's some model of the electrolyzer with predictive model. So this one is Gaussian process regression model. So previous one is theoretical, the dynamic model, but this one is if we have any data about this electrolyzer, how we can model it with kind of the regression model. So Gauss process regression model is assuming the mean value will be following the mean value of the data distribution. So this figure shows, the left figure show GPR Gauss model, and right one is a simple polynomial model. So the blue dots are the experimental data. It's not linear, obviously, and we are trying to figure out what's going to be power. The horizontal axis will be the power consumed, and the vertical axis will be the amount of hydrogen produced by this power input. So that's going to be the real data will be used to model this water electrolyzer. And that this two slide is about the price of electricity. When we buy it and sell it, its price will change and there will be some fluctuations. So the time is from 01 hour, 02 hour until 19 hour, 7 p.m. So there is a little Korean word. I didn't recognize this one when preparing the slide, but this one is actual, the electric power data from South Korea home trading website. So the resource is in the bottom. So the price of selling and buying also changing. So we have to figure out how we can utilize this information to operating our system. And this price model will be also the past data. So the past data is very useful to make decision and learning, but what we have to do is make decision about the future. So all past data, everybody can analyze and explain what happened, but predict out of this what may happen next time step and make a decision what we supposed to do. That's going to be in the area of artificial intelligence. We need help from the artificial intelligence. So the fluctuation in the future will be generally described in two different models. One is called random walk model. So with the noise coefficient epsilon with 100, 300, 500, you in the lower left corner with random walk model, the hydrogen price is fluctuating so widely. So that's going to be almost unpredictable. But more reasonable approach rather than this one is using the Brownian motion model from physics, and that's also called used in the financial market engineering to anticipate the stock price. So we have some mean value, and that mean value may increase or decrease, but some tendencies. And out of this, we add volatility with sigma. So that part will be describing the randomness of the model. So even though the Brownian motion price changes with different mean value, 1 and 2, 3, the fluctuation is still there, but it's more in the controllable and trend. So this will be what we really observe in the market. The price always changes, but it's not going to jump up and down like the random walk model in the left. So we use the Brownian model out of the past price data to anticipate what's going to be the next price in the future, tomorrow, the day after tomorrow, for the myopic future. So this is the part of the old module we modeled to integrate into green hydrogen production system model. Then what we need to is we need to make some operation strategy. The strategy is it's going to be driven by hydrogen demand, P of H2. The P of H2 is for the given specific amount of hydrogen, this is the power required to produce that amount of hydrogen. So we are going to describe all input output as the unit of power. So this power, demand power, will be determined by the ratio. First one, model one, is if photovoltaic, the power is good enough, then the demand. Our action will be the tuple triple on of the three elements. First one is we are going to use photovoltaic power only. And in case the photovoltaic power is not enough, but we also need electric storage power, then we are going to use photovoltaic power and also use battery power, P, electric storage system power. And second case is third case is even though both of these power, renewable energy attached with battery is lower than the demand, then we have to bring the grid power that's going to be sold in the tuple. So first one means, the action means if there is some value in the first element in the tuple, we are going to use that amount from photovoltaic system. And if there is any value in the second element in the tuple, we are going to that value out of the battery system. And third one is we are going to bring it from the grid system. So out of this, we are going to make the decision. Now, depending on the situation and time and change of the demand and price of the market, when we have to produce hydrogen, how much power should be from the renewable system or battery system or grid system. So basically, we are changing the distribution of the source power to generate hydrogen to meet the demand. So that's going to be what we want to do with AI. So we use operation model, the PPO and A2C and SAC as our deep reinforcement learning algorithm for managing this system. So I'm going to explain what they are in the methodology part. So all this reinforcement learning is based on fundamental theory of Markov decision process. This one is based on the state, the first variable state. What kind of action is possible? That's what we are going to choose. And each state and each action, there will be probability that will bring our system to next state in the next time unit. And there is also reward. When we do this in favorable way, we will get more reward. That's going to be described in number. Positive number, more reward, that implies to the machine that you are doing good. And if this reward is decreasing or go negative, that means what you did, chose an action for the state, is actually what we don't want. So this one is teaching the machine learn what is good and what is bad from a lot of set of the data. And the weight will be also experience-based scaling factor. So we can define a different reward system. The reward one is simply net profit. We want to sell our surplus power, and sometimes we also produce hydrogen, and that's going to be sold in the market with hydrogen price. And out of this, if we brought some power from the grid, we need to pay. So this is simply the revenue, what we earn, subtract what we pay, the cost. That's going to be the simple net profit objective. But second, reward function will be the hydrogen production itself. So the hydrogen production should be the cell sold in the higher price than electricity cell. That means if we have enough power from the renewable power source, if we change to hydrogen and sell it, that's going to be more profitable than just sell it to the grid and do not produce hydrogen. So that's going to be encourage our system to do more with more hydrogen production. And the reward function 3 is about renewable energy production. So instead of grid power, try to use as much as possible the renewable power rather than uh, from the hydrocarbon or nuclear power. So that's going to be our renewable energy concern reward. And rest one is will be similar to close to required H2, but I'm skip this one. So the different approach, out of different approach, what we used is policy-based running algorithm, and especially PPO, proximal policy optimization, and also actor critic variant of A to C and soft actor critic. Using this algorithm, we provide the data and plugged into our model and used this algorithm to figure out whether they are finding optimal approach, optimal decision or not. And all this module has been used in PyTorch, in Python code. So first one, PPO-based cases is, I'm going to skip this part, it's too much detail, but this is the three different AI algorithm we used for the application. So next chapter is about the verification and validation of model, if our model is correct and they are working as we intended, and when we plugged some real value, does they work reasonably, and we can explain them. So that's what we are going to do. So this is the real small size, the test field, and to apply our system model with renewable powers, electric power from the renewable energy, solar energies, and also there is a battery system connected, and fuel cell is used as the demand, and hydrogen tank was also used as demand, and there was PCV distributing the power from renewable source electricity, the battery simply, and the grid. So out of this, the some verification model means the best model was selected, and generating analysis code to verify the operation of DLR framework, and output graph against time step for window has been used 1, 10, and 100 as an example. And we tested 3 policy-based reinforcement learning algorithms, such as proximal policy and actor critic variant 2. So this one is the running result. After we plug in a lot of value, actually we used 500,000 iterations of data for training. Then the algorithm was able to find, in this specific situation, do this. The situation means the price of electricity to buy and sell, and price of the hydrogen, and also the limit specific amount of the battery level and the production level from the solar panel, and considering every possible combination of the environment, it's going to running. So this graph increasing to the upper right corner means it's going to run. What's the better way to make decision for various different situations? So after this graph is starting to saturate and stable with a pretty good high number, it should be the positive number because that's the reward. The vertical axis reward. That means this algorithm has been trained good enough to make the good decision. And in case of actor critic, soft actor critic A and C, the increasing speed was a little bit slow, and sometimes it reached maximum, but it didn't converge pretty well. So there was some fluctuation still. So this one is making learning, but it's not very useful. And A to C cases, it's running very fast. From the beginning, it's the reward function increase up to 18,000 level pretty quick, but there is also fluctuations, and sometimes there is an observation of failed learning. So we use the most stable PPO approach. It's going to learn relatively fast, and it's going to learn very well. So there will be, after it's run a certain level, it's not going to make a failure in this making decision. So this will be some comparison of experiment and simulation. I will skip this part and then go detail with the electricity. So this one is one example we use to verify our model is working. The first at the bottom is the demand of the hydrogen, how much power we need to produce good enough amount of hydrogen. And out of this, when we run our algorithm based on the photovoltaic power over time and some electricity, changing electricity, it's going to sometimes use the photovoltaic power to generate hydrogen. And sometimes it's going to use battery powered hydrogen system. And if both of them are not enough, it's going to bring the grid power, the third one with green color. And out of these three, if we add first three, photovoltaic and energy storage system and grid power together, the sum, the integration of three power will be showing very similar shape like our real demand. So it means once we recognize the demand, future demand, then we are going to distribute power between three sources appropriately. We have no idea why it happened this way, that way, but that is a way to maximize our goal, objective function, maximize the profit, for example. But anyway, the sum of these three power sources is good enough to meet the demand. That's what we found from our complex system. So it's working pretty well as a verification. So this is detailed view of the previous graph, and it's also showing it's meeting enough with our demand, but sometimes it's using the battery power, and sometimes it does not use battery power even though we have good enough battery level. It depends on the situation to maximize our profit. So I will explain why the portion of these three different power sources are determined in this way in the next case, next slide. So this one is again the conversion graph for verification. So I'll skip this one and this one. This one is the price. So price in the first graph is electricity prices, and the second one is when we buy it. And next to one, first one, green one is when we buy it, the price we have to pay to the grid system. And second, green one is if we have surplus power and sell it to the grid, that's what we earn. So we can sell our power and we can make earning. And third one is hydrogen prices. The hydrogen prices also changes over time. Daytime, in the morning, in the evening, it changes. So depending on what time we have to produce more hydrogen and sell it at higher price, and what time we have high prices when selling our electric grid, we have to make decision what's the best policy use, the portion of different ratio of three power sources. That's what algorithm is actually reinforcement algorithm is determining the portion of three power sources. So skip this one and I'll go to the result quickly. So we considered all reward R1, R2, maximizing the profit and meet the hydrogen production, increase the hydrogen production and environmental part and others. And we consider all of them together. We were able to show the case three. Considering all these different objectives together, the reinforcement algorithm we used, the PPO algorithm, was able to make the maximum profit. It was able to produce hydrogen. Case 3 is about 100 tons, metric tons, but the case 3 is a little bit low. But if we consider the net profit by selling and changing the distribution of different power sources ratios, the net profit is actually, this one is more. So as long as it's demand the minimum requirement of the hydrogen, this optimization algorithm was able to maximize their profit by determining the different power source ratios and determine when to sell and when to buy and when to produce hydrogen. So it's almost time. So I'm going to summarize the talk. So out of this work, first we were able to develop the complicated, sophisticated green hydrogen system model by modeling each module and combine them together as a system module. And we were able to verify its working with some real data, and we was able to show it's working. And the second one is out of a lot of 10,000 of iterations. Some data in the iteration was from the real experimental data, and some other data is from the government repository.